Hello guys, welcome to H2O, the A to Z of chemistry. I am Dr. Ritu Johar, your educator for this course, the atomic structure. Today we will begin with lecture 11 from the course, but make sure you have watched the previous ones before viewing this one. In the last lecture, we started a discussion about the spectra, wherein we discussed about the definition of the spectrum, then the classification into emission spectra and the absorption spectra. While discussing the emission spectra, we discussed by the end of the lecture the sodium spectrum, and now we are left with the discussion about the hydrogen spectrum, which we will be doing in this lecture. But before doing that, we would quickly wind up with the discussion on the absorption spectra, because that we are not supposed to do in a detail, but hydrogen spectrum, yes, you require a great detail into that, right? So we will begin with the absorption spectra. So what is absorption spectrum? Well, when a continuous electromagnetic radiation, this is passed through the vapors of an element or solution of a substance, and the transmitted light is analyzed by a spectrograph, dark spaces are observed which correspond to the light radiations absorbed by the substance. And such a spectrum obtained, this is known as the absorption spectrum. So let me explain you what we mean by this. We have the experimental setup, and according to this setup, we have a solution. We can take vapors of an element also, or a solution of a substance also. So here we have taken a sodium chloride solution. Otherwise, like if you want the vapors of an element, you could take that in a similar discharge tube as you took for the emission spectrum. The only difference over here is that we are not passing electricity through it. What we are doing is we are placing this in front of a light source. We allow a light source to pass through either the vapors of the element or through the solution of the substance. Some of the portion of the light will be absorbed by the solution, and the rest is going to be transmitted out. And what we are doing is we are analyzing this transmitted light here. This light, we allow it to pass through the prism and then onto the photographic plate. Fine. What do we find on the photographic plate is that this is a continuous spectrum, except that there are a few dark spaces seen in the otherwise continuous spectrum. And you will find this interesting, that wherever there are dark spaces in the absorption spectrum, there were bright lines in the emission spectrum. So the wavelength of the dark lines in the spectrum, they are the same as those of the wavelengths of the bright lines in the emission spectrum. And in the case of sodium chloride, if you remember, the two yellow bright lines, they were seen at what wavelengths? 5896 and 5890 Armstrong. So similarly, now in this absorption spectrum, you will see two dark lines at the same wavelength in an otherwise continuous spectrum. Okay. So the dark lines of the absorption spectrum, they are the bright lines of the emission spectrum. So I hope you can understand what is absorption spectrum now. And how do we differentiate between the absorption spectrum and the emission spectrum? I hope you can appreciate, but quickly just explaining it once again, we have the emission spectrum produced by the analyzing of the radiant energy emitted by an excited substance, whereas absorption, this is produced when the radiation, this is passed through a substance and the transmitted light is analyzed by spectroscopy. And then it consists of some bright lines separated by dark spaces in emission spectrum, whereas in the absorption spectrum, it consists of dark lines in otherwise continuous spectrum, right? So now we can move on to the hydrogen spectrum. This what we are studying is the discontinuous emission spectrum. So for the hydrogen spectrum to be studied also, the experimental setup you can see is what we had in the emission spectrum. So we've taken a discharge tube containing hydrogen gas. When an electric discharge, this is passed through the hydrogen gas, the hydrogen molecules, they dissociate. They are going to break up into atoms, and now these atoms, they are going to pick up the energy. They are going to move the electrons, they are going to move to the higher energy levels, and hence the hydrogen atoms are getting excited. And when these excited atoms, they would want to come back to the lower energy levels, they are going to emit the electromagnetic radiation of discrete frequencies. And on analyzing, you will find that there are several lines, several series of lines, in fact, which are seen in the hydrogen spectrum. And they are not only in the visible region, they are in the infrared region, the visible as well as the UV region also. Right? The visible you will be able to see on the spectrograph, but for the infrared and the UV, there have to be certain special techniques to visualize them. And these series, they have been named after their discoverers. So this we have the first 5 series of the hydrogen atom spectrum. And the entire spectrum, you can see there are lines and there are series of lines. Some lines, then there is a dark, quite a big dark area, then again some lines, and then again a big dark area. So these are series of lines, and they have been named after the discoverers. One in the ultraviolet region was discovered by Lyman, so this is called as the Lyman series. Then one in the visible region, the Balmer series. The infrared region, Paschen series, Brackett and Pfund series. And hydrogen atom, this is the simplest atom, and therefore this has the simplest spectrum. The spectrum of the other heavy elements, they are quite complex in nature. So that is why we study about the hydrogen spectrum and not the rest. We would leave that for the higher classes. So Balmer series, they fall in the visible region of the spectrum, and we can see them very well because they are the colored radiations. And what you will see is that the one with the longest wavelength, this is the red line, and it has a wavelength of 656.3 nanometer, and this is called as H alpha. Okay, the line with the longest wavelength of the Balmer series, this is H alpha with the wavelength 656.3 nanometer. The next line of the wavelength 486.1 nanometer, this is in the blue-green area, and this has called as H beta. The third line, the violet line, so this is in the region of what wavelength? 434.1 nanometer, and this is violet and it is called as H gamma. The fourth is H delta with the wavelength 410.2 nanometer. And as the wavelength decreases, what you will find is that these lines, they are coming closer together, but they become weaker in intensity, right? Now, Balmer was the first person who analyzed the hydrogen spectrum lines in the visible region, and he found a simple empirical formula to calculate the wavelength of all the lines in the visible spectrum of hydrogen. The relationship he found was that the wave number, this is equal to 1 by lambda, you know, and this value, what he found was that 109678 into 1 by 2 square minus 1 by n square centimeter inverse, where lambda is the wavelength and n, this may have integral values 3, 4, 5, etc. This equation is also called as the Balmer formula. and by choosing a particular value of n, the wavelength of a particular line in the spectrum that can be calculated. For example, when we take n to be 3, what would you get the wave number to be? On calculation, when you are just putting n to be 3, you will get this as 15,233 centimeter inverse and the wavelength to be 656.5 nanometer. So now this wavelength, this is falling in the red region, and we have defined this line to be the H alpha line, the hydrogen alpha line, the first line. And then we have N4, the wavelength of H beta. This comes up to 486.1 nanometer, which we've already seen in the spectrum. So these are the values of the wavelength, and they are coming through this formula. And then for n to be infinity, one obtains the limit of the series at lambda to be 364.6 nanometer. This is the shortest wavelength in the Balmer series, and beyond this limit, no further distinct lines appeared. Only a faint continuous spectrum could be seen. Right? So now Balmer formula, this gave only lines that appeared in the visible spectrum. There were wavelengths of the spectral lines in other series in the other regions which were found, observed by other people like the Lyman and the Bastian, Brackett and Fund. So they can be calculated by a more general equation called as the Friedberg equation. And this equation says that 1 by lambda is equal to R into 1 by n1 square minus 1 by n2 square, where n1 and n2, they are integers and they may assume values from 1, 2, 3 to infinity, with the requirement that n2 is always greater than n1. Right? So N2 has to be always greater than N1, and R, this is the Rydberg constant. The value of this is 109678. So that is the same. So there we are just putting it as R, the Rydberg constant. So as the other series of the spectra for hydrogen were discovered, they were represented by the formulae which is derived from the Rydberg's formula. So this Lyman series, N1 is 1. So the Lyman series 1 by lambda becomes R into 1 by 1 square minus 1 over N2 square centimeter inverse, and N2 would start from 2 to infinity, and the wavelength, you find this in the UV region. Then the Balmer series, N1 is 2, that we've already studied, and N2 will start from 3 to infinity. The wavelength coming in the visible region. Then the Bastian series, this N1 is 3 and N2 starts from 4 to infinity in the infrared region. The Brackett series, N1 is 4, N2 starts from 5 to infinity. Again in the infrared region, the wavelength comes, and the Fund series, N1 is 5, N2 is going to start from 6, again in the infrared region. So here is the chart showing all this. We have the name of the series, the Lyman, the Balmer, Bastian, Brackett and Fund. In the year these series were discovered, then N1 being for Lyman 1, Balmer 2, Bastian 3, Brackett 4, Fund 5, and N2 from the next integer up to infinity, and then the region. So now the simplest empirical formula of Balmer, this can be written in terms of frequency of light as well, because we now know that there is a relationship between frequency and wavelength. And what is that? Yes, that is C is equal to nu lambda, or we can say 1 by lambda. This is going to be nu upon C. So frequency we have by putting the value of 1 by lambda from the Balmer's formula. So we get frequency is equal to R into C multiplied by 1 over 2 square minus 1 upon N2 square or N square, right? So the spectra of only a few elements, which are called hydrogen-like species, they can be represented by the simple Balmer formula or the Rydberg's formula. So these hydrogen-like species, they include hydrogen itself, the singly ionized helium, and the doubly ionized lithium, because they will become isoelectronic. So they will have the same number of electrons as hydrogen itself. And however, these results, the formulas they are giving, from that what the wavelengths we can find, the frequencies we can find, these results, they do not give any idea why only certain frequencies they are observed in the hydrogen spectrum and other frequencies they are not observed. The emission spectrum of molecules, please do remember the emission spectrum of molecules, which we will call as the molecular spectrum. This is a band spectrum, and this is generally given by compounds or gases like nitrogen, oxygen at low pressure and temperature. And what does the spectrum consist of? It consists of a number of bright bands separated by dark spaces. And each band, it is sharp at one end, but gradually it fades as we approach the other end. So this is also called as fluted spectrum because of its fluted appearance. So I hope the hydrogen spectrum, this is clear to you all. And now this would be all for this lecture. We would be discussing about the Bohr's atomic model in the next lecture. If you have faced any difficulty in understanding anything, you want to contact us, you want to discuss anything about chemistry with us, please feel free to mail us at h2ochemistry@gmail.com. We would try our level best to revert back to your queries within a few hours, at the most 24 hours. Right? So if you've liked the lecture, please do click on the like link, that motivates us a lot. Also do subscribe to our channel H2O and click on the bell icon so that you get a notification as and when we put up a new lecture for you, a new course for you. So that would be all. Have a nice day. Enjoy your studies. Bye bye. Best of luck.